Yo, this is Naz.
And Allison. And this is the Gas Laws video.
Thank you for that lovely introduction, ladies. As promised, we're going to walk through a few examples to help us practice utilizing the various gas laws. As you can see up here, we have our combined gas law, ideal gas law, and then STP, standard temperature and pressure. And so to mimic the quiz conditions, we're actually going to walk through 3 or 4 practice problems that are mixed together, and we're going to walk through and help us decide which of the laws to use. Okay, so a few things to note. For a combined gas law, this is P1 times V1 divided by T1 equals P2 times V2 divided by T2. Anytime that we are working with temperature in a gas law, the preferred unit is Kelvin. So if you are given Celsius, you have to add 273 to convert it. If we're thinking about pressure, temperature, and volume relationships, pressure and volume have an inverse relationship, meaning whatever happens to one, the opposite will happen to another. Temperature has a direct relationship with each pressure and volume. So if temperature increases, pressure will increase. If temperature decreases, volume will decrease, and vice versa. Okay? Pivner, the ideal gas law, pressure times volume equals mole times R, which is a gas constant, and temperature. Things to note here, volume has to be in liters. Has to be. The pressure and the R value are related. The R value, which is a fixed constant, it's either one of these two numbers. It depends on whatever unit is provided for pressure. So if pressure is provided in ATM, we'll plug in this number. If it's provided in kPa, we will plug in this number. If it's not provided in either one of these units, then we're going to have to convert using these amounts here. Okay, STP, standard temperature and pressure, these are set conditions that we can use to compare lots of different gases. If something is at standard temperature and pressure, or STP, we assume that the temperature is 273 K or 0 degrees Celsius, and 1 atmosphere or 101.3 kPa or 760 torr millimeter mercury. And this is the important part. 1 mole of any gas at STP will be equivalent to 22.4 liters. So this is a volume unit. So as you can see, we have a little double mole mountain here with 2 little balloons for liters in gas. So let's first look at our first problem, and then based on what information is there, help us decide which of the formulas or steps to use. It says, what volume of chlorine at STP is necessary for the complete reaction of 4.81 grams of sodium? There are a couple of red flags here. Number 1, I've provided a reaction. Number 2, STP. Anytime that you see STP, you should be thinking 22.4 liters. Okay, so now our next decision is this a single mole mountain or is this a double mole mountain problem? Because I have, if I am annotating, I've got 4.81 grams of sodium, which is Na, and then it's asking for volume of a different substance, chlorine in this case. This is a double mole mountain. So I'm going to do a quick little double mole right up. I'll do it right down here. And, you don't have to be this extra on your quiz, but I'm gonna do it for the tube. So here we have to decide who mountain 1 is. It's always whoever the number is. So 4.81, we're starting at grams of sodium. Sodium is Na. And we're working towards volume, which is liters, of chlorine. And make sure that you're using Cl2 because it's a diatomic. So next, how many steps this problem will be? This will be 1, 2, 3 steps. 4.81 grams, and I'm going to make sure to put my units here because it's double mole. So we got grams Na. I'll probably speed through this part. Alrighty, and we're back. As you can see, we set it up just like a regular stoic problem. The only thing different between this and the other double mole mountain problems is this right here. Anytime we have volume in liters, our conversion factor is going to say for every 1 mole we have 22.4 liters. And again, that's because this is at STP. So let's now look at a different problem. Alright, so this says the commercial airliner has an internal pressure of 1 atm and a temperature of 25 degrees Celsius. If the temperature of the airliner drops to 17 degrees Celsius during the flight, what is the new cabin pressure? So there are a few red flags. One, I don't see anywhere in this problem STP, so I can eliminate that we are doing this over here. Next, I need to decide if we're using combined gas law or the ideal gas law. The fact that this says new cabin pressure, that's indicating to me that pressure changed, which means we need initial and final values. Okay, this also has nowhere, it doesn't mention anything about the mole or grams or anything like that that would hint to me that this would be a Pivnert problem. So we are going to use the combined gas law. P1 V1 over T1 equals P2 V2 over T2. Okay, and the next thing I want you to do is to list out your variables. P1 V1 T1 P2 V2 T2. Can you even see all of this in the... Alright, readjust force. Okay, perfect. So as we can see here, we're going to go through. We have 1 atm, and it says that it has an internal pressure if the temperature of the airline drops. So that is a hint to me that these are initial values. So that means equals 1 atm, temperature 25 degrees Celsius. If it says the temperature drops to 17 degrees Celsius, oops. Oh, pardon me, that says 17 degrees Celsius, guys. During the flight, what is the new cabin pressure? Well, note here that volume is not mentioned at all. Okay, it is not in the problem at all. This also applies if something says that it's constant, then you don't have to include it. We're just going to completely eliminate V from our equation, which means that our new formula is P1 divided by T1 equals P2 divided by T2. So let's set this up. P1, which is 1, divided by T1. So this right here, it's in Celsius. We have to add 273. So 273 plus 25 is going to give us 298. Equals, we don't know the second pressure, over, again, 17 plus 273, 290K. So from this step, you can solve it algebraically any way that you want to. I'm just going to show you how to do it by cross multiplying and dividing, just because I know a lot of students find that pretty easy. So numerator of 1 times the denominator of the next. So 1 times 290. 290 equals 298x. To get x by itself, we need to divide both sides by 298 so that this can cancel. We're left with x. We do it to one side, we have to do it to another. From this step, we're just saying 290 divided by 298. X equals 0.97. The unit, we were looking for a pressure. My initial pressure was an atm. Okay, and also, to see if this makes sense, we know that pressure and temperature have a direct relationship. Okay, so if we see that temperature decreased, that means that that pressure should also decrease. And it did. It went from 1 to 0.97. This answer makes sense. All right, let's keep trucking along. My gosh, this is a struggle, y'all. Okay, so next problem. It says how many milliliters of N2 gas are present in a 100 gram sample of a gas at 800 millimeter mercury and 20 degrees Celsius. So again, our first step, let's eliminate who we know it is not. It is not STP. It does not say anywhere in this problem that it is STP. Therefore, we are working between combined gas law and Pivnert. Something that should stick out to you is the fact that you see gram. Okay, gram, something that we can convert to the mole. The only place in either of these equations that could work would be for this N. There is nowhere here that mentions anything about a gram or a mole. Also, remember, this equation is used for when we see a change in a gas. This is straight up, it is what it is. If this is the pressure, if this is the temperature, how many of milliliters are we going to have, okay? So we can eliminate this down to Pivnert. So let's go ahead and list out our variables. P, V, N, R, T. And I'm going to go through and give things a temporary home, all right? We are going to have to do some conversions here because we know we have preferred units. Pressure right here. Oh, y'all, this whole time I've been making this, and y'all can't even see my bad. So here, with Pivnert, P, remember, can be in ATM, millimeter mercury, torr, kPa. Volume has to be in liters. N is the mole. We can convert, from or to, but this is going to be the mole. R, depending upon the P, and then temperature has to be in K. So, I see this, 100 grams. That best fits right here with N. 800 millimeter mercury, that is pressure. Okay, 20 degrees Celsius, we know that is a temperature. And then the other unit I see is milliliters, which is a volume. We know that volume is measured in liters, so we know that there's going to be the conversion at the end. The R, based on the P unit. The only two R values that I've provided for you are an ATM and kPa. We see millimeter mercury here. That should be a red flag that you need to convert that pressure unit before you plug in an R. Again, I don't care which one you convert to. I think it's easiest to convert to ATM. If you have millimeter mercury and you want to convert, you're trying to get rid of this unit. It needs to go on bottom to cancel. Okay, on top is the unit you want. In this case, let's choose ATM. For every 1 ATM, I have 760 millimeter mercury. Okay, it's the same for torr. When I put this in my calculator, you're basically saying 800 divided by 760, which is 1.053 ATM. Because we have ATM, we are now going to plug in this unit for R. Okay, so now let's convert our other units so that we can go ahead and plug into the equation. This is in grams. It has to be in mole before we plug it in. Gram to mole, one conversion. Gram on top, gram on bottom. For every 1 mole of N2 gas, we have its molar mass, 28 grams. That's 14 times 2. When I plug that into the calculator, 100 divided by 28, I get 3.571 moles of N2 gas. Finally, temperature at 273, so we got 293 K. Now let's plug into the equation. Pressure times volume, we don't know that, equals N R T. Okay, so we reduce this side. This becomes 1 x. Multiply all of these. We get 3.571 times 0.0821 times 293. You get 85.901. Get x by itself. Okay, 81.578. Now, one thing to note here is that this is in X's preferred, this is in V's preferred unit, which is liters. The problem is asked for milliliters, which means I need to convert. If you're going from liters to milliliters, remember there are more milliliters. There are 1,000 milliliters for every 1 liter. We have to move this decimal 3 times to the right. If you were going from milliliters to liters, you would move it 3 times to the left. So this is equivalent and that's my final answer. Alright, and then let's do one more. When I read this problem, it says, what is the volume of a 250 gram sample of CO2 at STP? Again, I'm looking for red flags. Is there a change happening? Are there multiple units of the same type of measurement? Are moles or grams mentioned? And if so, is it at STP? Red flag here is STP. So I'm looking for units. 250 grams, and then I see volume. Next, is this a single or a double mole mountain? This has to be a single mole mountain. 1, I don't see a reaction. Number 2, I'm only working with one compound. Okay, this is asking about one thing. So this is just a simple, my little balloon for liters. We always start wherever the number is. So that's 250 grams. It asks for volume, which is liters. So this is 1, 2 steps. And now y'all do your stoic thing. We have grams here, mole, liters. Mole is going to be 1, liters, 22.4 liters for every 1 mole at STP. Grams is the molar mass of CO2, which is 44 grams. Plug this into my calculator, so we're looking at 250 times 22.4 divided by 44. My final answer would be liters.